Okay, so today I want to extend what we were talking about last time, where we illustrated some of the calculations in two dimensions, two space-time dimensions. Here I want to talk about, today I want to extend this a little bit and talk about conformal symmetry in two Lorentzian, two Minkowski space, two-dimensional Minkowski space, R1, and then we'll extend these ideas to more than two dimensions, and this will lead us to the conformal Killing equation for general d-dimensional spacetime, and we will solve this and write down the conformal Killing vector in a general d-dimensional spacetime, and then I will, in particular, finish off today, I think, by trying to count the number of independent parameters required to parameterize such a conformal Killing vector. And of course, you will remember what we did in the last lecture, or I think the lecture before that. But this will then tell us what the dimension of the conformal group is in d dimensions. Okay. So let's continue then. Starting off in two-dimensional Minkowski space, so this is R1, so let's take, in, let's say R1, and taking the metric eta mu nu to be the diagonal metric +1, -1, and you can see that, when we go to higher dimensions, I'm going to be using the mostly minus signature metric, so that'll be +1, -1, -1, etc. With this, the conformal Killing equation reads, as usual, d mu, let's say zeta nu, plus d nu zeta mu equal to d naught zeta naught minus d1 zeta 1 eta mu nu. Remember, there was this factor here. It's coming from this d dot zeta piece, and of course there's no prefactor because we've chosen d equal to 2, so that gives us the prefactor of 1. So now I have mu and nu as free indices in the story, and I get to choose which ones to work with. So I'm going to start off by setting mu and nu equal to 1, in which case I get d1 zeta 1 plus d1 zeta 1. That's two d1 zeta 1s, and then I've got one of those on the right hand side that will cancel. And I said what? Okay, so let's do this explicitly. So this would be 2 d1 zeta 1 on the left hand side, and on the right hand side, eta 1 is -1, so that exchanges this sign here, so that becomes d1 zeta 1 minus d naught zeta naught, and this will take out one of these factors, so that the result there is that d naught zeta naught plus d1 zeta 1 is equal to 0. That's one equation. I'm going to keep this in mind now. And the second equation I will get from setting mu equal to 1, say, and nu equal to 0. And here, because the metric is diagonal, there's no right-hand side. And so we learn that we learn that d1 zeta naught plus d naught zeta 1 equal to 0. So these are two equations and two unknowns, and we can solve them. We can solve them by differentiating and going to a higher order equation. So if I do that, I'll find that if I differentiate the first one with respect to, let's label these guys 1 and 2. If I differentiate the first one with respect to d0, and then the second one with respect to d1, and then I subtract, I find that the following is true. D0 squared zeta naught minus d1 squared zeta naught is equal to 0. And then we recognize that, actually, let me ask you, does anybody recognize this equation? Anyone? Don't be shy. Frank.
Well, it would look like a Laplacian, but with a change in sign from the metric.
What do we call that? What is this equation called then, if it's a Laplacian with a change in sign and metric?
No idea. Wait.
What TB?
It's
TB had an answer.
It's the wave equation.
It's the wave equation. Thank you. So this is the wave equation in R1, 1. Okay. Excellent. And we know how to solve the wave equation. The wave equation we've learned how to solve since we were in kindergarten. And this basically tells me that I'm cutting out the in-between steps here, because again, everybody knows how to solve the wave equation in 1 + 1 dimensions. There's many ways to do it. One way to do it is to go to what I call light cone coordinates. We will do this a little later in another slightly different context. But for now, I'm going to read off the solutions. Again, this should not be unfamiliar to anyone. And the solutions are that zeta naught of, let's say, x1, or x0 and x1. Sorry, let me be consistent. x0, which is time, and x1 is the sum of two functions, let's say f and g, they're arbitrary functions, of x0 plus x1 and x0 minus x1. Similarly, zeta 1 is the difference of these two functions, f of x0 plus x1 plus g of x0 minus x1. These are what's known as the right moving waves and left moving waves. And they're solutions of the wave equation that basically say if I've got some system like a string and I vibrate the string, then I'll produce two waves. There will be left moving waves, right moving waves, f and g. In other words, but we're not really interested in solving the wave equation here. We're interested in understanding how this ties up to conformal symmetry. So what we're saying here is that the conformal transformation, is specified by two real functions, the left and right moving waves. And this matches the number of parameters in a one complex function that we found in R2. So in R2, which is isomorphic to the complex plane, we found that there were two parameters in two real parameters in one complex function that specified the solution. Here we find two real functions, f and g. Okay, so these two real functions two real valued functions specify the formal transformation. Okay, so these correspond to left movers and right movers. So and you'll recall that in two-dimensional Euclidean space, we found that actually, it was an enormous symmetry that was specified by any holomorphic function. And that's matched in the two-dimensional Minkowski space by the fact that these functions f and g are completely arbitrary, right? All we know is that f plus g and f minus g, f plus g and minus f plus g will specify the solutions completely, but those are still arbitrary functions. Okay, so this gives us some insight, at least in a setting that we should be familiar with, two dimensions, for what to expect in the higher dimensional case. So let's go to a general d-dimensional spacetime. So what we want to do again is to analyze the conformal killing equation in a general d-dimensional spacetime. So to act with, I'm going to start off with the conformal killing equation, and then I'm going to act on them with two derivatives. So in a general d greater than 2 spacetime, solve the conformal killing equations. I'm going to abbreviate that conformal killing equation as follows. We'll start off by differentiating. And what I'm doing here is I'm imitating what we did in 2 dimensions. So by way of reminder, the conformal killing equation reads d mu, say psi nu plus d nu. You know what, I'm going to do zetas. Zeta mu plus d nu zeta mu equal to 2 over d d dot zeta times eta mu nu. Right? So that was what the conformal killing equation looks like in the general d-dimensional spacetime. So what I want to do now is I'm going to differentiate this with respect to d mu, d nu on both sides, d mu, d nu, and then try and simplify. So I've got a d mu d nu acting on a d mu zeta nu. Sorry, it should be a nu. Okay, I'm going to move this derivative to act on this guy, I can commute these derivatives here. So I'm going to move the new derivative to act on the new. And then this new acts on this new here, and this mu can act on this mu. So on the left-hand side, I will get d mu, d mu, d mu, d mu, acting on d nu zeta nu, plus d nu d nu, acting on d mu zeta mu. On the right-hand side, I get the eta contracted with these two derivatives, which makes it into 2 over d mu, also acting on d dot zeta. And you can see that d dot zeta was precisely this guy here is exactly what we were calling either of these guys. And then I don't really care what these indices are here. I'm summing over them in any event, so they're dummy indices. And d mu in a general d-dimensional Minkowski spacetime is what I would call the Laplacian. So this says that twice, the D'Alembert acting on d dot zeta is equal to 2 over d times the D'Alembert acting on d dot zeta. Or another way of saying the same thing is that d minus 1 D'Alembert acting on d dot zeta is 0. Okay, so this is the equation of interest to us. It's a simplification of the conformal killing vector equation in d dimensions. And this tells us that as long as d is not equal to 1, this equation tells us that the D'Alembert of d dot zeta is equal to 0. So if d is not equal to 1, and remember d equal to 1 is the very special case of a 0 plus 1 dimensional space-time or quantum mechanics. So this is a system that we actually care about from the point of view of learning some lessons, but conformal symmetry is special there. But as long as d is not equal to 1, it follows then that what this means is that D'Alembert is equal to 0. So let's label this guy equation 3. We'll come back to it just now. So that's the first one. All right. Then if you remember this game that we played, where we took the killing equation and we differentiated with this once with respect to, let's say, d lambda. And then we changed labels. So we found there that d mu, d lambda zeta nu plus d nu zeta lambda is equal to 2 over d eta nu lambda d mu d dot zeta. And then we just permuted the labels and kept track of them so that the next equation was d lambda of d mu zeta nu plus d nu zeta mu was equal to 2 over d eta nu mu d lambda of this guy. And finally, d nu of d lambda zeta mu plus d mu zeta lambda. It's 2 over d, eta mu lambda, d nu of d dot zeta. So let's call this 4, 5, and 6. And then if you remember what we did, we went 4 plus 6 minus 5. So 4 plus 6 minus 5. So 4 plus 6 minus 5, which gives us a combination that looks like this: 2 d mu d nu of d dot zeta is equal to 2 over d 2 d nu d mu plus eta mu nu times the D'Alembert acting on d dot theta. Okay. There's factors of 2 that I can cancel on the left-hand side and the right-hand side of this expression. And then I can use equation 3, this equation here, which tells me that the D'Alembert acting on d dot zeta, this guy here, for example, vanishes. So that tells me that this whole term here vanishes, which leaves me with the following. So what we find then is that 1 minus 2 over d of d mu d nu on d dot zeta is 1 over d eta mu nu box is 0. Okay. So now we notice that d equal to 2 is special, but we knew that already, because when d equal to 2, if d is equal to 2, then the factor in brackets here vanishes. But if d is not equal to 2, then this equation is true if and only if d mu d nu of d dot zeta is 0. So this says that the second derivative of this guy d dot zeta is 0, which means that d dot zeta must be a polynomial of degree 1. Is everybody with me? Good. So if d is not equal to 2, it follows that d dot zeta is a polynomial of degree 1 in x mu, i.e., we can write it as d dot zeta equal to, and now I'm going to write things in a slightly funny way, but it will become clear in a little bit. 2 b dot x plus lambda times d. Okay, so this is a slightly strange, if you look at it for the first time, way of writing what I'm calling a degree 1 polynomial. So this is why it's degree 1. It's linear in x, and this is just the coefficient of that linear part. Okay. And then this is the intercept when x equals 0. So this is the slope, x dependence, and the intercept. And this minus sign and this factor of d here are there for convenience. It's because I know I'm going to need to have something looking like this in a little bit. So now this is equation 7. This. Okay. So this gives us a parameterization for d dot zeta. But remember, we're not really interested in just d dot zeta. We're interested in zeta itself. But now we can act with the second order operator d nu on the conformal killing equation. And remember what we found is that so acting with d nu on the conformal killing equation, and if we simplify a little bit, okay, so we want to do the same thing again. So we want to act with the d nu on the conformal killing equation and then relabel, and then go the same as this 4 plus 6 minus 5. We will get 3 equations. They will look like this. D, let's say alpha, d beta, because I'm running out of indices, d mu zeta nu plus d nu zeta mu equal to 0. I will get that d alpha d mu d beta zeta nu plus d nu zeta beta is equal to 0. And I will get that d alpha d nu d mu zeta beta plus d beta zeta mu is also equal to 0. So where are we? 8. So let's call this 9, 10, and 11. And then we go 9 plus 11 minus 10 gives me that, with some simplification, d alpha, d beta, d nu zeta mu is equal to 0. So this tells me that zeta mu has to be at most a degree 2 polynomial. Okay. And if I substitute back into the conformal killing equation, then I'll find that d so substituting back into formal killing equation, we'll find that d, let's say rho of d alpha zeta beta minus d beta zeta alpha is equal to d alpha d rho zeta beta minus plus d beta zeta rho minus d beta d rho zeta alpha plus d alpha zeta rho. And that's equal to d alpha of 2 over d eta rho beta times d dot zeta. Sorry, just give me 1 second. Okay. So that's d alpha of 2 over d eta rho beta of d dot zeta minus d beta on 2 over d eta rho alpha d dot zeta, which when I substitute back for where was it? When I substitute back for d dot zeta in equation 8, I get minus 4 b alpha eta rho beta minus b beta rho eta rho alpha. Okay, so this is just a little bit of manipulation and organizing indices. So don't worry too much about it. It's in my notes, and Jacob will scan these and upload them. You can take a look at the details. I have skipped out 1 or 2 steps here. The key point here is that I have an equation now on the left-hand side that looks like d rho of something. On the right-hand side, I have this equation involving b's, which are the constants, the slopes, and etas. So they're just constants. So I can integrate this now once, and I'll find that the following is true. So integrating. I find that a half of d alpha zeta beta minus d beta zeta alpha is minus 2 beta alpha x beta, b alpha x beta minus x alpha b beta plus some omega beta alpha. And then from the killing equation, so let's label this guy. That's 12. Okay. So all I've done is I've integrated this equation here once with respect to x rho, and that's where I get the x's from. And I have accounted for all the minus signs, and this guy here has to be antisymmetric in the 2 indices. I still have 1 more equation to account for, and this is from the conformal killing equation, which gives me an equation for d alpha zeta beta plus d beta zeta alpha. So we know from the conformal killing equation that a half d alpha zeta beta plus d beta zeta alpha is minus eta alpha beta 2 b dot x plus lambda. I'll call this equation 13, I guess. And now if I add 12 and 13, I get that d alpha zeta beta is omega beta alpha minus 2b alpha x beta plus 2x alpha b beta minus eta alpha beta times this 2b dot x plus lambda. Okay. And now remember, I'm trying to solve for zeta. So now I can integrate once more. I get that zeta alpha, say, and I'm choosing to write the index upstairs now, it doesn't really matter, is some constant a alpha plus omega alpha beta x beta. That comes from this term here, which is a constant. So it's going to give me something linear in x, minus lambda x alpha. Again, lambda is a constant, so linear in x, plus x squared, x dot x, beta alpha, the alpha index is carried by, sorry, b alpha, the alpha index is carried by b, minus 2b dot x times x alpha. So this thing is quadratic in x, as is these two terms are both quadratic in x. And that's it. That's the solution of the conformal killing equation. And the result is something that we call a conformal killing vector. So now we have to unpack this killing vector a little bit. Remember, the killing equation tells us about the symmetries that it's trying to describe. So if we were trying to solve the conformal killing equation, this is telling us about conformal symmetries. So this is called the conformal killing vector. And it encodes information about the types of conformal transformations that are allowed. So following what we did in 2 dimensions, let's count the number of independent parameters in this solution. Sorry, this is the conformal killing vector in d dimensions. And you can see that, conceptually, it's not much more difficult than what we did in 2 dimensions, but it's a little bit more tedious to keep track of the indices and differentiate and integrate and then differentiate again, take derivative, take some linear combinations and then integrate again. So you have to keep track of the indices as you're doing these things, but it's basically just playing around with differential equations. So it's a first order differential equation and you want to solve this first order differential equation. Okay, so now we have the conformal killing vector in d dimensions. The question is how many independent parameters are there in this solution? And remember, the number of independent parameters in the solution will tell us about how many generators there are in the conformal group. So let's see. In d dimensions, then, so the question we want to ask is how many independent, that's the key word here, how many independent parameters parameterize this solution? Okay, so in d dimensions, we have the following. We have lambda, this guy here. Okay, and that's just one number. So lambda gives us 1. Right? We have this a mu constant here. And in d dimensions, alpha gives me d possible numbers. So there are d numbers in here. So a mu corresponds to d such numbers. Then I have b mu, this vector b mu. And b mu also corresponds to d numbers. It's a d vector in d dimensions. And then finally, I have this antisymmetric omega mu nu, which is a d by d matrix, d by d antisymmetric matrix. And so it has a half d times d minus 1 independent entries. And we can go ahead and count how many in total. So this means that the total number of parameters that we need to specify a conformal killing vector in d spacetime dimensions is 1 plus 2d plus a half d times d minus 1, which is d squared minus d plus 4d plus 2 all over 2, which is a half d plus 1 times d plus 2 independent parameters. Okay, so I'm going to stop here today. And then next time we'll talk about what each of these different parameters correspond to. And then we'll do this by looking at the finite version of each of the above transformations. And that will take us through to the statement, at least, of the conformal algebra. Okay, so thanks very much. And I will see you guys on Friday, hopefully in person. Any questions?